In this section, we are going to discuss about the definition of linear transformations, several examples, and what they look like in the finite dimensional case. All right, if we consider two vector spaces V and W, a transformation T from V to W is actually in fact just a fancy word for function or vector functions, which means T will transform every vector in V, make them become some vector in W, all right? And so T transform X in V into Y in W. Now, the important thing is that for every X in V, there will be something in Y associated to the X. And that Y is going to be unique, one and only one. You cannot have something like 1x corresponding to 2y's in W. And we are going to write y equals t of x. If t is a transformation from V to W, then t is called linear if it preserves the addition structure and the scale structure in between the two spaces. Geometrically, if you have two vectors x and y, then you are going to have the summation of x and y computed by the parallelogram. The transformation T will transform x into Tx. The transformation T will also transform y into Ty. And of course, the transformation T will also transform the sum vector of x and y into some other vectors that we call T of x plus y. And you see that for a general transformation, what we end up having may not be a parallelogram. And that means that for a general transformation, the sum of Tx and Ty may be different with the vector T of x plus y. If you want T to be a linear transformation, first it will have to do this. And at that time, sum of Tx and Ty turns out to be the same as T of x plus y. Also, we'll need the transformation to preserve the scale as well. For example, if you consider some vector that is twice as long as the vector x, 2x, then the transformation T will also transform 2x here into something that we denote as T of 2x. All right, and that T of 2x will have to be twice as long as T of x. In other words, the transformation must preserve the scale that we originally have in V. So next, we are going to consider several examples, and we will explain briefly why they should be linear transformation. First example, the rotation about the origin in the two-dimensional space, the xy plane, is a linear transformation from R2 to R2. Why? Because you know that the rotation preserves the distance and the angle. So it will transform a parallelogram into another parallelogram. And so the diagonal of the first parallelogram will get transferred into the diagonal of the resultant parallelogram. And because the parallelograms are preserved, the summation will be preserved as well. So that's why it preserves the addition structure. Now, of course, it will preserve the scale. If you have something twice as long of something, after the rotation, you still have something twice as long as the corresponding image here. And so rotation is actually a linear transformation. The reflection across the line in the xy plane is also a linear transformation, because you know that reflection will preserve the length and the angle. It will preserve the geometry structures, especially the parallelograms, so it will carry all the addition structure into the addition structure. And of course, the scale will be the same as well. If you consider a matrix A of size am by n, and define a linear transformation T of X being computed by multiplying the matrix A with the column vector X. Then the newly defined transformation T is in fact a linear transformation from Rn to Rm. Why is it from Rn to Rm? That is because if you want to multiply the X and the A successfully, the number of columns in A and the number of entries in X will have to be the same. And because A has n columns, that means the number of entries in X will be n entries. And so X is in Rn. The T will transform an Rn vector into some vector that we denote as T of X. That vector has to live in Rm because A has m rows. If you multiply A and the column vector X, the resulting matrix will be a column vector, but only has m entries. Now, why should it be linear? If you consider T of X plus Y for any X and any Y, then it's the same as multiply the matrix A with the column vector. That is the result of X plus Y. But then we already know that we have the distributive law for matrix vector multiplication. This equals to AX plus AY. But then what is AX? AX is the formula that you use to compute T of X. Right? So this is going to be the same as T of X. AY is the formula that you use to compute T of Y. And so you have successfully proven that T preserves the addition structure. Right. Now, if you consider T of R times X, where R is the scalar being multiplied to the column vector X, then it's actually computed by multiplying A with the column vector. That is the result of multiplying the scalar R to the column vector X. Now we know that we can pull the scalar out in front and multiply A and X first, and this is done by the scalar law. And then that is why T preserves the scale structure. Now let's consider something more abstract. The differentiation. We know that the differentiation will transform a function into its derivative. Why the differentiation is a linear transformation? You have to check D of f plus g. Then what it does is finding the derivative of f plus g. But you know that the derivative of the sum is the sum of two separate derivatives. And the derivative of f is actually d of f. The derivative of g is d of g. And so we have successfully proven the addition property here, right? Similarly, we can find the derivative of the scale of f. It's the derivative of Rf. And we have learned from calculus 1, it is going to be R times f prime. And so that equals to R times d of f. So we have successfully proven the scale property here. So the differentiation is a linear transformation. The identity transformation from any vector space V into itself, defined as IV of x equals x, which means that this identity transformation takes in vector x and spit out exactly the same thing. So it does nothing. Turns out it is linear transformation. Why? Because if you plug in x plus y, you should get x plus y. But what is x? Well, x is IV of x. And what is y? It is IV of y. So it preserves the addition structure. And similarly, you can see easily that it preserves the scale. So this is trivially a linear transformation. We have seen in this example that if we start from a matrix and define a linear transformation by the matrix vector multiplication, then we end up having the transformation being linear. The fact is much nicer if we start with any transformation from Rn to Rn. You don't know exactly what it is, but there will always be a matrix that will make the formula for it. This is what we are going to discuss next. And it's in fact theorem 3.1. And this also called the matrix representation theorem for linear transformation, which says for each linear transformation from the finite dimensional space to a finite dimensional space, there always exists a matrix A that represents or that makes the formula for T. Moreover, if you can find a matrix A, that's the only one you can find. All right. So every transformation, there is only one matrix that represents it. All right. So let's first prove the theorem. So Tx is in fact T of a column vector. Now, next we are going to split this vector into the sum of simpler vectors because T preserves the addition property. So this is going to be next because T a linear transformation. So it also preserves the scale structure. That means T of x1 times a vector is going to be the same as multiplying x1 with T of that vector. So we can pull x1 out in front of T. Similarly, all right. So what are T doing? The T is transforming every vector in Rn into an Rm vector. So T of these vectors are going to be vectors in Rm. All right. So that means I can go ahead and rewrite this as x1 times some column vector in Rm. So I'm going to use a1, a2, am. Then I'm going to do the same with this one, right? So it's going to be x2. I want to write a1, a2, am again, but that comes up with some problem here. Because I wouldn't know whether this column and this column will be the same or not. We are going to add some second index to differentiate them. So this is the first one. So I will add the number 1 after the first index. This is the second one. So I will add the number 2 as the second index. And then we can continue doing so until the last one. And because this is the nth vector, so we add the n as the second index. This, in fact, is the multiplication of the matrix whose columns are these column vectors with the column vector of x1, x2, xn. This is going to serve as the matrix A that we claim we'll be able to find at the beginning. And this is actually just the column vector x. We have proven the existence of such matrix A. The question left is whether that is unique or not, right? So prove the uniqueness of A. Now you have seen how we prove the uniqueness in vector spaces. We assume there is something else that we denote as B, say. And we are going to try to prove that A and B are equal, right? Because we have already found A, so this implies that B of x would equals to A of x for all x in Rn. Now here come the tricks of how we utilize the word for all. For all means that the equality is true for any choice of x that you're gonna make. Because this is true for all, so it has to be true for x being 1, 0, 0. This implies that B times 1, 0, 0 equals A times 1, 0, dot, 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 0. But then by the observation that we made from the definition of matrix vector multiplication, when we multiply a matrix with a column vector, it's actually just the linear combinations of the columns of the matrix using the scalar provided from the entries of the column vector. So this is the same as multiplying 1 with the first column of B, and then 0 with the second column of B, and then 0 with the last column of B, which is the nth column. Right? On the right hand side, you perform the matrix vector multiplication. So 1 times the first column of A, and then 0 times the second column of A, and then up to 0 times the last column of A. Well, you are going to have a bunch of 0, 0, 0, 0s here. The only thing that is left is that 1 times the first column of B equals 1 times the first column of A. But isn't it the same as saying that the first column of B equals the first column of A? And then we can repeat this for the second axis, 0, 1, 0. And then we repeat that until the last axis, 0, 0, 0, 1. Right? And we are going to have the matrix B equals to the matrix A because all of their column turns out to be the same. And we are done. Right? We prove the existence and the uniqueness. Next, let's consider several examples of how we are going to use theorem 3.1 to find the matrix representation for these transformations here. Right? We have 4 examples, and the last one I asked you to read at home. Identity transformation on Rn. So remind that the identity matrix from a vector space, general vector space V into V, is the one that is defined by IV of x equals x for all x in V. So that implies if you want to find the identity transformation on Rn, that is going to go from Rn to Rn, and that is defined as Rn of x being x for all x in Rn. Now we are going to again utilize the word for all to identify the matrix that represents this transformation. All right, if you understand the proof, the idea of the proof is this one. You split any general vector into the sum of the bases, the standard basis. And then you find what T does on the standard basis. Yeah. These will constitute the columns for the matrix A that you are looking for. All right, so this is what we are doing in practice. To find such matrix, we compute T of the standard basis and then put them into columns. And these are going to be the matrix A that you are looking for. So because this is true for all x in Rn, so it has to be true for x being the first vector in the standard basis. For this vector, we have Rn of this vector. And you can see that it will do the same for the other choices. So the first column of the matrix A is, of course, going to be the first vector you found. The second column is this one, until the last column, which is this one. All right, so you can see that the matrix that represents the identity transformation on Rn is in fact an n by n matrix, whose entries on the diagonals are all ones and the entries outside of the diagonal are all zeros. This matrix, in fact, has a special name and special notation for it. We call it the identity matrix and denote it as the I stand for the word identity. And instead of writing n by n, we know that for any identity matrix, it represents the identity transformation, which is going from a vector space to itself. So there is no need to write n by n. We actually just write in. Okay, so next we are going to consider the second example. the rotations about the origin in the xy plane. So xy plane is in fact another way of saying R2 is a linear transformation. We know that. Now find the matrix representation for it. Example number 2. Let's consider the rotation of an angle, say phi. Of course, this rotation is going to be from R2 to R2, the plane to the plane. So in order to find the matrix representation, we have to find t of the standard basis, which is t of 1, 0 and t of 0, 1. Right? And then those are going to make the column vectors for the matrix we are looking for. All right, so we have to look at this one. This is the vector 1, 0. Well, if you do the transformation t, then you would end up having this vector, which is denoted as t of 1, 0. Now you want to find its coordinate, right, which is xy. How do you find xy? Well, first of all, because it's the rotation, it will protect the length. And because the length of the initial vector is 1, the length of the resulting vector is going to be 1 as well. The angle is phi. And we have learned from geometry, x is going to be the length times cosine of phi. And y is going to be the length times sine of phi. All right. So that is going to be equals to cosine phi, and y is going to be sine phi. So we found the first column, right? Next, we are going to look for what it does on the second vector, the second unit vector here. This is the vector 0, 1. And under the transformation, this is what we are going to get. T of 0, 1. Length is 1. Now, if you want to find the angle here, that is going to be this angle, which is phi, at an angle of 90 degrees or pi over 2 radian, right? And if you want to find the coordinate, x prime and y prime, then x prime is going to be the length, which is 1, times cosine of the angle. Now remember, the angle is the big one, which is pi over 2 plus phi, right, which is cosine of pi over 2 plus phi. And y prime is 1 times sine of pi over 2 plus phi. You multiply 1, so you actually just get sine of pi over 2 plus phi. So this implies that x prime and y prime equal to cosine of pi over 2 cosine phi minus sine of pi over 2 sine phi. And for the sine of sum is going to be sine of pi over 2 cosine phi plus cosine of pi over 2 sine of phi. And so that helps you compute x prime, right? Remember, cosine pi over 2 is 0, so this is 0, this is 0, this is 1. So you end up having minus sine phi and y prime as cosine phi. So t of x is going to be the same as the following matrix multiplied with x. And that matrix is, the first column is right here, cosine phi, sine phi. The second column will be negative sine phi, cosine phi. And this is the matrix representation for the rotation. Now let's consider this one, the reflection across a line passing through the origin in the xy plane. So reflection t from R2 to R2. It will take a vector in R2 and transform it into another vector in R2. Okay, so you have the xy plane. And you have a line passing through the origin. Usually the line will be y equals a times x. That's the Cartesian equation of the line. However, when you deal with rotation and reflection, it's easier to work with the polar coordinate equation of the line. Theta equals phi. It turns out that the equation y equals a times x is actually the same as y equals tangent of this angle phi times x. The slope A is tangent of the angle formed by the line and the horizontal axis. In R2, its standard basis consists of two vectors. 1, 0 that we usually call vector I, and 0, 1 that we usually call vector J. We want to compute T of vector I, which is T of 1, 0. See what it is, right? And then we want to compute T of vector J, which is T of 0, 1. See what it is, and then arrange them into the columns for the matrix representation. Now let's work on this one first. If you take the reflection of vector I across this line, this is going to give you this vector, which you denote as T of vector I. Because the vector I has length 1, after the reflection, the length is preserved, so you are going to have length 1 here for this one as well. Now you want the angle, because if you know the length of the hypotenuse and the angle here, then the adjacent side here is going to be just the hypotenuse multiplied with cosine of the angle. All right, so what is the angle here? Because you start from here, you reflect it. So the angle from the horizontal axis to the red line will be the same as the angle from the red line to the resulting vector. So you have gone phi, and then you have gone another phi. So this should be twice as large as phi, 2 phi. And so this is going to be equal to 1 times cosine of 2 phi. And the y coordinate is going to be 1 times sine of 2 phi. We get the first column. Now we move to computing the next one. So this is going to be vector j. Now you reflect it over the red line. So this is what you are going to get. And we denote it as T of j. In order to find its coordinate, say x prime and y prime, well, you need to first know the length of the vector here. But because it was the result of the reflection of the j vector here, the length here and the length here will be the same, but this is the unit vector, so the length is 1, so the length of this one is again 1. Now you need to know the angle from the x-axis to the vector. What is this angle? I'm going to put it as question mark, and we are going to solve for question mark. Because we know that the vector tj and the vector j are symmetric across the red line. So the average of question mark with the angle here, which is pi over 2, right? J is pi over 2. If you take the average, it has to be the line that is in the middle of them. So that is going to be phi. And from here, you can easily solve for the question mark being 2 phi minus pi over 2. You know the angle here, and you know the length of the hypotenuse of the right triangle here. In order to find the horizontal coordinate, you multiply cosine of the angle, which is 2 phi minus pi over 2. And then to find the vertical coordinate, you multiply sine of the angle. So the matrix that represents T we have the first column being this column, right? So that has to be cosine of 2 phi, sine of 2 phi. The second column will be cosine of this and sine of this. If you compute that, that's going to give you sine of 2 phi. If you compute it, it's going to give you negative cosine of 2 phi. That's the matrix that represents the t. Double check. Consider the reflection over the y-axis. That means that the phi you need to consider is 90 degrees, pi over 2. Right? This is the y-axis. The angle that formed from the horizontal axis to the reflection line is going to be pi over 2. Well, that means 2 phi is going to be pi. And so the t that represents the reflection is actually just the following matrix. Cosine of pi, sine of pi, and sine of pi, negative cosine of pi. Multiply with an x. Well, cosine of pi is negative 1. Sine of pi 0. And so negative of negative 1 is 1. And for every x, it's actually just the column vector of two components x1 and x2. If you really perform the matrix vector multiplication, what you end up having is negative x1, x2. So remember, this is the same as you write t of x1, x2. And t is the reflection across the y-axis. Well, is this true? All right. So let's consider this. Now the reflection is across the line here. Now if you were going to consider the reflection of a vector on the tip of the vector here, x1, x2, this is your vector capital X. This is gonna be t of capital X. And see, guess what you are going to get here? You take the reflection, which means that the distance from here to this is going to be the same as the distance from here to this. So if this is x1, this is negative of x1. Of course, x2 stay the same. All right, that means your vector tx is going to be negative x1, x2. Exactly what you get with the matrix representation. Now we are going to talk about finding the matrix representation for a linear transformation, where we only know some pieces of information that t transform the three vectors here into the three vectors here, respectively. We know that in order to find the matrix representation for t, we need to know t of the standard basis, which means you have to find t of 1, 0, 0. And then you will have to find t of 0, 1, 0. And then you have to find t of 0, 0, 1. Right? I know that we are working with three-dimensional because we were given t on the three-dimensional vectors here. So t is going from R3. Where is it landing? It is going from R3. What are the results that we get? Where are they living? The result that we get after the transformation t are living in R2. All right, so that's why I know that t is going from R3 and ends up being in R2. Back to the discussion, we need to find t of this, and t of this. We know no information except the three results here. So in order to find t of 1, 0, 0, you have to somehow utilize t of this, and t of this. To do that, we'll first represent 1, 0, 0 as a linear combination of the three vectors in R3. Then, because of the linearity property, we can draw this as then. What is T of this one? It was given to be 1, 3 plus B times. What is T of 1, 1, 0? It was given to be 1, 4. And then plus C times. What is T of this one? 1, 1. Then this is going to be like A times 1 plus B times 1 plus C times 1. And then below you have A times 3, B times 4, C times 1. Now, in order to solve for A, B, and C, you know that you are going to solve a system of linear equations because this is like 4A plus B plus C equals 1. 7A plus B equals 0. And 3A equals 0. You solve for A, B, and C. That's possible, right? That's just computation. And then you repeat the process with 0, 1, 0, and repeat with 0, 0, 1. You have to solve three systems. Right? Now we need to come up with another way to get this one done faster. Well, why don't we do this? Instead of having to do that for a specific vector and then repeat the whole process again, I'm going to just write x, y, and z. So we'll have to solve the following system. So the augmented matrix is going to be, and then you are going to row reduce it to the row reduced echelon form. So this is going to be your A. Of course, this is going to be your B, and this is going to be your C. Oh, by the way, I need to correct this one as well. We are working with x, y, and z. A general one. All right. So from here, we know that T of any x, y, z is going to be 1/3 of z A plus B plus C, right? So 1/3 of z plus this guy and plus this guy. For the second one, 3A, 4B, and C. And then you simplify, combine the like terms. What you end up having would be x minus z x plus 3y minus 22 over 3z. So this is the formula for the transformation T. It will take a three-dimensional vector into a two-dimensional vector by the formulas here. Now, we are asked to find a matrix representation for it. There are two ways to get the matrix representation from here. The first way, we are going to go exactly as in the theory. We compute T of 1, 0, 0, knowing that x is 1, y is 0, and z is 0. So you replace x being 1, y and z are 0. You are going to get 1, 1. And then you repeat that with 0, 1, 0. This means that x is 0, y is 1, z is 0. And so you plug in here and compute, you should get 0 and 3. And then you compute the last column. So that has to be -1, -22 over 3. So T of x is going to be the same as multiplying the following matrix. 1, 1 being the first column, 0, 3 being the second column, and this one being the third column. Multiply with the x vector. Now, method number 2, to get the matrix representation, we can go directly from here. Okay? So T of x is going to be the same as T of x, y, z. It is going to be, as we computed, x minus z, and then x plus 3y minus 22 over 3z. Now we are going to perform as if we are finding the spanning vectors for some vector space, right? So we are going to split x out of y, and then split y out of z as well. So 0y, 3y, and then plus negative z, negative 22 over 3z. And then we are going to pull x, y, and z out as the scalar. It's the same as multiplying the matrix, whose columns are the vector. Multiply with the column vector, whose entries are the scalar. That's how we define the matrix vector multiplication, right? And so this is going to be the matrix representation for T. Proposition 3.1. The linear transformation will transform line segments into either line segments or points. So you have a point A and a point B. Of course, they will form a line segment between A and B. Then the linear transformation T is going to take A into T of A, which we will denote as A prime. And it will take B into something that we will denote as B prime, which is T of B. And so between A prime and B prime in the new space, they will automatically form a line between A prime and B prime. Now the question is, if you have a point C in between A and B in the previous space, will it get mapped into in between A prime and B prime in the target space? Intuitively, this should be true. If a point C is in the middle of A and B, then there will be some number T in between 0 and 1 that will represent the C as 1 minus T times A plus T times B. When T is 1, C coincides with B. When T is 0, you get C coincide with A. And for example, if T is 1/2, then you will have 1/2 of A and 1/2 of B. That means the middle point. Now, under the transformation T, the point C will get mapped into C prime, which is T of C. But then C is the linear combination of A and B. Then using the linearity property of T, knowing that 1 minus T is just a scalar and T is just a scalar, A and B are vectors, we are going to have this equals to 1 minus T times TA plus T times TB. And so C prime is going to be equals to 1 minus T times TA is A prime and TB is B prime. And look, if you can represent C prime as the combination of A prime and B prime in this way, then it's got to be in the middle of A prime and B prime. Here are two cases. If A prime coincides with B prime, then the whole line segment has been mapped into a single point that is A prime. Now, if A prime and B prime are different, two distinct points, then the line segment AB under the transformation T will get mapped into A prime B prime.